Hey, what's up guys, this is Dr. Vivek Palipuram bringing you the next lecturette in ENGR 250, Probability and Statistics for Engineers and Computer Scientists. In this lecturette, I'm going to discuss tree diagrams which are used to solve problems pertaining to the law of total probability. Specifically, tree diagrams are very useful to solve those problems wherein you perform an experiment which is composed of multiple sequential sub-experiments. So by drawing the tree diagrams, essentially what we are doing is we are enumerating what are the outcomes of these individual sub-experiments and how these outcomes lead to subsequent other outcomes when you perform the other sub-experiments. The final leaves in this tree diagram are going to be the outcomes of the entire experiment. In this tree diagram, you'll be drawing branches. These branches will be labeled with probabilities and conditional probabilities associated with these sub-experiments. To find the probability of any outcome, which happens to be a leaf in the tree diagram, we trace the path from the root of this tree all the way to that given leaf, and we multiply the probabilities along the way to find the probability of that particular outcome. This theory which will become much more clear when we actually see some tree diagrams in action. So as I mentioned before, the tree diagrams are used to solve those problems where you have an experiment which is composed of multiple sub-experiments. The tree diagrams that you will draw, it will have branches which are labeled with probabilities and conditional probabilities. The leaves of a tree diagram are going to be the final outcomes of the entire experiment. If you would like to find the probability of any one given outcome, you trace the path from the root of the tree all the way to this outcome's leaf and multiply the probabilities along the way and find its probability. As an example, consider an experiment which is composed of two sub-experiments which are performed one after the other. Sub-experiment 1, and then after that I perform sub-experiment 2. Further assume that sub-experiment 1 has two possible outcomes, A and B, and sub-experiment 2 has two possible outcomes, L and let's say H. So when I draw my tree diagram, here's how I'm going to draw the tree diagram. Everything starts at the root. Since I'm performing sub-experiment for 1 first, I'm going to have two possible outcomes. Either I will get A or I will get B. Probability of getting an A will be noted on this particular branch, and probability of getting a B will be noted on this particular branch. At this point, I would have completed my sub-experiment 1. Next, I need to perform sub-experiment 2. Let's say that I got A first when I perform my sub-experiment 1. When I perform sub-experiment 2, I can get either an L or I can get an H. This branch will be labeled with the probability of getting an L after I get an A. So this branch will be labeled with probability of getting an L given that I got A first. So this branch is labeled with probability of L given that I got A first, and this branch will be labeled with probability of H given that I got an A. Similarly, let's say that I got B the very first time. So next time when I perform sub-experiment 2, I will get either L or an H. This will be labeled with probability L given B, and this is probability H given B. The leaves of this tree are these guys right here, and these represent the total outcome of the entire experiment. Specifically, this leaf here is A and L. This leaf here is A and H. This leaf here is B and L. And similarly, this leaf right here is B and H. So these are the final outcomes. To find the probabilities of these outcomes, what I'm going to do is I'm going to trace the path from the root to these leaves, and I will multiply the probabilities that appear along the way. So for example, if I want to find the probability of A and L, I'll trace the path from the root all the way to that leaf, and I'll multiply the probabilities that appear along the way. So probability of A times probability of L given A. Similarly, to find the probability of this leaf, I'll multiply probability of A times probability of H given A. Similarly, this one will be probability of B times probability of L given B. and probability of this leaf will be probability of B times probability of H given B. So this is how you'll obtain the probabilities of different outcomes in a given experiment, which is composed of multiple sub-experiments. Sometimes the events that we are interested in, the events for which we would like to find the probabilities, they may be composed of multiple outcomes, meaning that multiple outcomes may constitute a given event. In such a case, to find probabilities of such an event, we add the probabilities of those outcomes. Specifically, let's say that I'm interested in an event which corresponds to these two leaves. In order to find probability of such an event, I will add the probabilities of these leaves. So if your event resides in multiple leaves, then obtain its probability by adding probabilities of those leaves. So if an event corresponds to these two leaves, then I'm going to add their probabilities to get the probability of my event. Let's put this theory into action. This is the problem that you have already performed in your previous lecturette. You have three machines, B1, B2, and B3, producing resistors. B1 produces 80% acceptable resistors, B2 produces 90%, and B3 produces 60%. In an R, B1 produces 3,000 out of 10,000 resistors, B2 produces 4,000 out of 10,000, and B3 produces 3,000 out of 10,000 resistors. And I need to find the probability of getting an acceptable resistor. So let's solve this using tree diagrams. When you consider this problem of picking a resistor and checking whether it is acceptable or not, it is actually composed of two sub-experiments. The first experiment is to choose a machine for getting a resistor and then checking whether that resistor chosen from a given machine is acceptable or not. So there are two experiments here. Choose a machine, that's sub-experiment number 1. So that's my sub-experiment number 1. And then check resistor. That's my sub-experiment 2. So my tree diagram is going to comprise of these two sub-experiments. There's something interesting about tree diagrams, and that is the depth of the tree is equal to the number of sub-experiments. So depth or tree depth is equal to number of sub-experiments. So in this case, the depth of my tree is going to be equal to 2. As follows. First, I choose, everything starts at the root. I choose a machine first. I can choose machine B1 with probability 3,000 out of 10,000 because 3,000 resistors out of 10,000 corresponds to B1. I can choose B2 with probability 4,000 over 10,000, which is essentially 0.4. I can choose B3 machine with probability 0.3. If I were to choose B1, I will get an acceptable resistor with probability 0.8. That's what is given to you. B1 produces 80% acceptable resistors, and it's going to be defective with probability 0.2. Whereas B2 produces 90% acceptable resistors. So if I were to choose B2, probability that the resistor is acceptable will be 0.9, whereas it's going to be defective with probability 0.1. Similarly, B3 produces acceptable resistors with probability 0.6, so it's going to produce a defective resistor with probability 0.4. I am interested in acceptable resistors. First, let's denote these leaves. So this leaf right here is B1 and A. This one is B1 and D. This is B2 and A. This is B2 and D. B3 and A, and this is B3 and D. I'm interested in probability acceptable resistors. Now, my acceptable resistor is actually residing in multiple leaves. I have an acceptable resistor right here. I have an acceptable resistor right here, and I have another acceptable resistor right here. So my event acceptable resistor resides in these three different leaves. So in order to find this probability, I need to add the probabilities of these leaves. And further, to find the probabilities of these leaves, I need to trace the path from the root all the way to these leaves. So for example, probability of B1 and A is going to be 0.3 times 0.8, giving my 0.24. Probability of B2 and A is going to be 0.4 times 0.9, giving me 0.36. Probability of B3 and A is 0.3 times 0.6, giving me 0.18. So I will add the probabilities of these leaves, and I'll find that I get the same answer that I got initially when I solved this problem previous time, and that is 0.78. So that's how you apply your tree diagrams. You carefully read the problem statement. You identify how many sub-experiments are being performed. The depth of the tree is going to be equal to the number of sub-experiments that you're performing. Lay out your tree diagram appropriately. Label the branches with the relevant probabilities by carefully reading the problem statement, and then find the probabilities of the leaves. Your event of interest is going to be comprised of multiple leaves. To find probability of the event of interest, just add the probabilities of those leaves that correspond to that event of interest. That's all there is to it for the tree diagram. And if you carefully observe here, I have implicitly applied the law of total probability by adding these probability values. Let's work on another example. Let's say that a machine produces photodetectors in pairs. Tests show that the first photodetector is acceptable A1 with probability A3. So it's going to be defective with probability 2/5. When the first detector is acceptable, the second is acceptable with probability 4/5. If the first photodetector is defective, D1, then the second photodetector is acceptable with probability 2/5, and I need to find certain probabilities. I would like for you guys to pause your video here and try to draw a tree diagram for this problem statement. Carefully read the problem statement and identify how many sub-experiments are being performed, then lay them out in the form of a tree diagram. Once you're ready, you can unpause the video and I can show you how this can be done using a tree diagram. Okay, I hope you guys got the chance to solve this problem using the tree diagrams. This experiment is actually composed of two sub-experiments, where sub-experiment 1 is to check the first resistor. It's going to be acceptable or defective. Then the second sub-experiment is to check the second photoresistor. It's going to be either acceptable or it's going to be defective. So everything starts at the root. You check the first photodetector, it's going to be acceptable or it's going to be defective. Reading the problem statement, first photodetector is acceptable with probability 3/5. So this probability is 3/5. If this probability is 3/5, then that means that the probability that the first detector is defective will be 2/5. If the first detector is acceptable, then the second one will be either acceptable or it's going to be a defective one. It's given to you in the problem statement that with the first detector is acceptable, the second is acceptable with probability 4/5. So when the first one is acceptable, the second is acceptable with probability 4/5. So it's going to be defective with probability 1/5. However, if the first detector is defective, then it's going to be acceptable. The second one is going to be acceptable with probability 2/5. It's given to you in the problem statement. If the first detector is defective, the second is acceptable with probability 2/5. So that's that probability, which means that the second photodetector is going to be defective with probability 3/5. Because D2 is the complement of A2. Okay, so that's my tree diagram and these are my leaves. This leaf is A1 and A2. This leaf is A1 and D2. This leaf is D1 and A2. And this one is D1 and D2. Let's find out what we need to, let's see what we need to find out here. First, I need to find the probability that exactly one photodetector of the pair is acceptable. So I'm going to look into these leaves and find out which of these leaves have exactly one photodetector that is acceptable. Oops, I have two photodetectors acceptable here, so I will not consider this case. I have exactly one photodetector acceptable here. So this is a valid leaf for that event. I have exactly one photodetector here. So that's another leaf that is valid for this event. So probability of exactly one acceptable is equal to probability of A1 and D2 plus probability of D1 and A2. So I just add probabilities of these leaves. Now to find the probabilities of these leaves, I'll trace the path from the root all the way to these leaves. So the probability of the first leaf here, A1 and D2, is 3/25. Probability of D1 and A2 is 4/25. And when I add these probabilities together, I get 7/25. So that's the probability of for part 1, exactly one acceptable. The next one is find the probability that both are defective. Both have to be defective. So this is the leaf that corresponds to both defective. So probability of both defective is equal to probability of D1 and D2, and that probability will be obtained by tracing the path from the root all the way to that leaf. So that probability is 6/25. All right. Now let me ask you this question. Using this tree diagram, tell me what is the probability that at least one photodetector is acceptable? You can give me this answer during my WebEx office hours. As an example, let's work on one more problem. Let me show you one more problem as an example so that tree diagrams are finely ingrained in your minds. And then I'll give you a problem to solve for your Thursday's class. In this example, let's say that you have two biased coins A and B. A comes up heads with probability 1/4 and B comes up heads with probability 3/4. You do not know which is which, so you flip them both one by one, choosing the first coin at random. What is the probability of two heads? You can pause your video here, find out how many sub-experiments there are. The number of sub-experiments will correspond to the depth of the tree diagram. Draw the tree diagram and label the branches with appropriate probabilities. Your event probability of two heads will be either one or multiple leaves. Okay, so I hope you guys got the chance to look into this problem. Let's find out how many sub-experiments there are. There are actually 3 sub-experiments because I do not know which coin is which. So I choose the first coin and then I flip it. Then I choose the next coin. So my entire experiment is choose a coin. So that's my sub-experiment 1. Then I flip it. That's 2. Then I flip another, which is remaining. Flip the other coin. That's sub-experiment 3. So number of sub-experiments is equal to 3. So tree depth will be equal to 3. Tree depth will be equal to 3. Let's see. Everything starts at the root. First experiment, I choose a coin. I do not know which is which, so I choose a coin at random. So I can choose either A or B. Since I have no bias in coin selection, probability of choosing an A is 1/2. Probability of choosing B is also 1/2. If I choose A, I flip it. I can get either a heads or I can get a tails. For A, I get heads with probability 3/4. I get tails with probability 3/4. I get heads with probability 1/4 and I get tails with probability 3/4. Then I need to flip the other coin, which happens to be B in this case. So when I flip B, I can get either HB or TB. I get HB with probability 3/4, TB with probability 1/4. Similarly, I need to denote the branches here for this particular outcome. So I can get HB or TB with probability 3/4 or 1/4. But let's say that I choose coin B first. When I flip it, I'll get either HB or TB. I'll get HB with probability 3/4 and TB with probability 1/4. Then I flip the other coin, which happens to be A now. So I'll get either HA or TA. HA or TA with probabilities 1/4 and 3/4 respectively. So these are the leaves of my entire tree. And if you carefully observe, the depth of the tree is equal to 3. Level 1, level 2, and level 3. This leaf right here is A and HA and HB. This is A and HA and TB. If you notice here, I have dropped the intersection sign just for brevity because I do not want to spend too much time drawing that intersection. So this one is A and TA and HB. This one is A and TA and TB. This is B and HB and HA. This one is B, HB and TA. This one is B, TB and HA. And this is B, TB, TA. I'm interested in probability that both are heads. In order to find this probability, I will look into these leaves and find out or identify those leaves where I have 2 heads. I have 2 heads here, I have 2 heads here, and that's about it. These are the only 2 leaves that have 2 heads. So to find the probability that both are heads, I'll add the probabilities of these leaves. And to find the probabilities of these leaves, I will trace the path from the root all the way to these leaves and multiply the probabilities that appear along the way. So 1/2 times 1/4 times 3/4 gives me 3/32. And probability of this leaf here is 1/2 times 3/4 times 1/4, also giving me 3/32. So I get my final probability answer as 3:16. That's the probability of getting exactly 2 heads, or probability of getting both heads. Now, let me ask you this question. What is the probability that you get at least 1 tails? You can give me this answer in my WebEx office hours. What is the probability of getting at least 1 tails? For your Thursday's class as in-class participation problem, which you need to turn it in Canvas, I would like for you guys to solve this problem using tree diagram. Traffic engineers have coordinated the timing of 2 traffic lights to encourage the run of green lights. With probability 0.8, a driver will find the second light to have the same color as the first. Assuming that the first light is equally likely to be red or green, answer these questions. So please solve this problem using tree diagram. Carefully read the problem statement and find out the depth of the tree. And draw your tree diagram and find the probabilities of parts A, B, and C. I think it's a good time to stop this lecturette right here. Thank you for listening.